Hello everyone, we'll discuss semiconductor. Well, everybody knows about conductors like iron, copper, aluminum. You also know about insulators. Insulators like plastic, glass, wood. But in this chapter, we are interested in semiconductor. And why are we interested in semiconductors? Because there are certain properties which we'll see which help us in establishing something like on and off very easily. We can have a system, imagine a switch, which you can easily switch on or switch off very rapidly and very conveniently using something called semiconductors. And this property of on and off is nothing but 1 and 0, which is binary system. And in this binary system, I hope you know that all computer languages are written. So this semiconductor is something which is going to help us in establishing all that knowledge of binary system. But let's first understand meaning of conductors, semiconductors and insulators. You must be having a brief idea about that. We define energy levels or energy bands like valence band, conduction band, for any substance. What is valence band? In which electrons are tightly occupied in their orbits close to the nucleus. What about conduction band? Conduction band means electron can easily conduct. If it can move freely, then it will be called what? Conduction band. So where do you expect conduction band? Far away from the nucleus, so that attraction of the positive charge on the negatively charged electron is very less. This height is showing energy, total energy, which is sum of kinetic energy and potential energy. So this diagram tells us that in normal situation, energy of valence band is less, energy of conduction band is more. Band means collection of energies, bandwidth, collection of energies of all the electrons which are present close to the nucleus. Conduction band, energy of all those electrons which are free effectively from the nuclear attraction is the energy of conduction band. In conductors, let's show this whole thing in terms of width. So when you talk about conductors, what happens? This band, valence band, and this band, conduction band, they basically overlap. Overlap means there are energies which are in the valence band as well as in the conduction band. So you cannot easily distinguish between an electron whether it belongs to conduction or it belongs to valence band. It can easily switch from these two places, between these two places. So if you have an electron in any conductor, it if is in the upper range of valence band energy and is in the lower band of conduction band energy, then it belongs to both. That means with very slight input of energy and even without any input of energy, it can move from one position to another position, and therefore if it moves and enters into this conduction region, the moment it enters into this, it will be called free electron. And you know that these free electrons, they, once you connect a conductor, across a conductor, if you provide a battery source of voltage, then these electrons will start moving, forming a current. For conduction, for conductors, these things are quite easy. It's very easy for an electron to jump between these. When we talk about insulators, this is your conduction band and this is your valence band. Energy gap between these two is very large. So, it is almost impossible for an electron to jump from this into this. Therefore, there are no free electrons available. That means no current can flow through an insulator. In extreme situations, you can do if you increase the temperature very high. If you increase the temperature, you are basically increasing kinetic energy. If you are increasing energy, that means you are increasing the width, and therefore after some time it will definitely overlap. But those are very high extreme temperatures, or you apply a very powerful potential difference, very high voltages if you apply, then an insulator can conduct. But in normal situation, this energy gap is so large that any electron present in valence band will never find enough energy coming from thermal collisions or coming from the photons which come and strike these electrons. But all these interactions, they don't have sufficient energy, so for an easy transfer of electron from valence band to conduction band. And therefore these things are called what? Insulators. Now when we talk about semiconductors, for semiconductors, again these things do not overlap, but the gap is small as compared to insulators. Since this energy gap is small, you need less energy at room temperature. In semiconductors, you can find electrons which can jump from this to this, and therefore they will participate in flow of charge developing a current, but not that many as are present in a conductor. But still, it's easier to develop current easier with respect to an insulator. It's difficult with respect to a conductor, but we're talking about comparison between these two. So as compared to an insulator, it's relatively easy to provide enough energy to an electron which is present in this energy region. Once a photon comes, strikes an electron, it may get enough energy so that it can jump from this into this, forming a current because of free electrons. Now, this less requirement of energy can be regulated if we insert some impurities which are called donor or acceptor impurities. We'll see that. The point is, if we have a pure semiconductor, for example, we'll see this also, if we have a silicon crystal, which is a pure one, then this gap is large. But if we insert some impurities in a pure silicon crystal, then we further reduce this gap, and depending on the concentration of impurities, we can easily regulate flow of current. And if you can easily regulate flow of current, then that is what we are interested in. In conductors, we cannot easily control flow of electrons. The moment you connect a battery, there are plenty of free electrons, they start moving, developing a very high current. But based on the concentration of impurities and type of impurities, we'll see that part, we can regulate flow of current in semiconductors. This property is something which is very much useful in development of computers, calculators, basically any integrated chip type of thing. Draw these figures and then we'll write few statements and understand everything about semiconductors. Write down few statements. In conductors, valence band and conduction bands, overlap, and therefore electrons can easily move from valence band into conduction band, thus becoming free electrons. Resistivity of conductors is very low. Resistivity of conductors is very low, almost of the order of 10 to the power minus 8. You can write this also in the bracket, of the order of 10 to the power minus 8. Whereas in insulators, whereas in insulators, energy gap between valence band and conduction band, energy gap between valence band and conduction band is very large, and therefore and therefore at normal temperatures and therefore at normal temperatures no electron can jump from valence band into the conduction band, from valence band into the conduction band, and therefore free electrons are not available, and resistivity is very high, and resistivity is very high, almost of the order of 10 to the power 8, 10 to the power 9. That kind of resistivity is present. So resistivity is 10 to the power minus 8, and over there it's about 10 to the power 8 or 10 to the power 9. Quite a drastic change in resistivity. But for semiconductors like silicon and germanium, but for semiconductors like silicon and germanium, this energy gap between valence band and conduction band, this energy gap between valence band and conduction band is not that large, and therefore it is possible that at room temperature an electron of valence band, an electron of a valence band can jump into conduction band, and because of this few free electrons are available, and there is one more thing, holes. We'll see that free electrons and holes. Because of that, free electrons and holes are available, and therefore its resistivity lies between those of conductors and insulators, of the order of 10 to the power 1 or 10 to the power 2. So it is between those of conductors and insulators. Now let's see how this energy part is going to explain concept of current flow. Now let's understand the way current flow takes place in a semiconductor. Very easy to understand is silicon, and I hope everybody knows that in the outer orbit of silicon there are 4 electrons. Atomic number is 14, innermost 2, then 8, and then in the last one there are 4. These 4, they form covalent bonds with nearby silicon atoms. So effectively you get something like this. That's how a silicon structure looks. Every silicon atom is going to form four covalent bonds. This, this, and this. Thus completing 8 electrons in the outermost orbit, and therefore it becomes quite stable. So that's how silicon crystal looks. Now, energy difference between valence band and conduction band for silicon is roughly 1.12 electron volts. That means if you give an electron of valence band this much energy, it will jump and enter into what? Conduction band. This much energy it can get after an interaction with an incoming photon. So you know that all the electromagnetic radiation which is present all around, a photon coming from that interacts with one of these electrons. The moment photon comes and interacts with this electron, what it does, if it can give it this much energy, then this electron will move out. Move out means it will move and enter into what? Conduction band. It is now far away from the nucleus. The moment it comes out, it becomes what? Free electron. And if it exits this place, it creates a vacancy over here. This is that electron. It was present over here and now it's out here. It creates a vacancy, and because of this vacancy, now this silicon has what? Positive charge. So with the interaction of a photon, you got a free electron and a positive charge. So another photon will interact with this, it will leave this place, creating another free electron, and this silicon will become what? Positively charged. Let's focus on these two. But remember, photons are interacting and therefore positive and negative charge separation is happening. Now, this silicon, which is positively charged, is called a hole. This electron is called free electron and this is called a hole. Why this is called a hole and what's special about it? Let's concentrate on that. Once silicon is positively charged, this electron finds that this place is more attractive. Out here for this whole setup, system is neutral. But this electron finds that this silicon, this position is positively charged. Not necessarily this electron, it can be this also. So once this silicon electron finds that instead of this place, if it goes to this position, it has positive charge and therefore it will be more stable. So once it makes a transfer from this position to this position, this silicon atom becomes what? Neutral. This electron has moved over here. Since this electron has left this position, this silicon atom becomes now what? Positively charged. So what you can see, in conduction band, these free electrons are present and they are randomly moving. They are free. They are randomly moving in what? Conduction band. But at the same time, these electrons which are jumping from one silicon atom to another, fundamentally movement is of these electrons. But these electrons are in which energy band? They are still in valence band. This electron, when it was present over here, it is participating in a covalent bond. This electron is still in valence band, but it finds this place more attractive and therefore makes a jump. And the moment it moves and occupies this position, it makes this silicon atom neutral and this silicon atom positively charged. So, movement is of electrons, but these electrons are a bit different from these. These free electrons are moving in conduction band, but these electrons are moving in valence band. Just to easily distinguish between these two, instead of using movement of electrons, we now say that in this direction an electron is moving, but instead of saying this, we'll say that a hole which is positively charged. A hole which is positively charged is moving in this direction. No positive charge in reality is moving between two silicon atoms. It is still movement of what? Electrons. But these electrons are present in what? Valence band, and therefore instead of calling electrons, we are using the other system of positively charged holes. So very important statement or a short answer question is in front of you. Electrons, free electrons, the movement takes place in which band? Conduction band. Whereas movement of holes takes place in which band? Valence band. Note down this and tell me, are you comfortable with this part that holes are in valence band and electrons are in conduction band? Write down yes or no. One of you is asking the whole interpretation again. Every silicon atom has 4 electrons in its outer orbit. It makes 4 covalent bonds, thus completing 8 electrons in the outer orbit and acquiring most stable energy pattern. But then energy difference between valence band and the conduction band. When electron is present over here, when it is participating in a covalent band, energy over here, and when it jumps and makes itself free and moves into the conduction band, that energy difference is only of 1.12 electron volt for silicon and 0.70 for germanium, then it can easily acquire this much energy if it interacts with a photon. So suppose a photon collides with this electron, it gains enough energy, at least this much, and then goes out in the conduction band. So once this electron goes out, we call it free electron. Because of the movement, silicon is now positively charged. This silicon, which is positively charged, makes this position a little bit more attractive. So these electrons, which are part of valence band, they find that if they can move from this position to this position, then things will be more stable. And that is true also. But the moment it moves from this position to this position, this silicon becomes neutral and this electron finds that it is now back to the same situation as it was when it was present over here. But nonetheless, because of the movement of the electron, this electron was participating in what? Valence band. It was forming a covalent bond. It is still doing the same thing, and therefore we say that this electron is moving in that energy band which is called what? Valence band. But because of the movement of electron, now this silicon has a vacancy and it creates what? A positive charge. Fundamentally, the thing which is moving is an electron. This is also an electron, and these two electrons are completely identical. So how do you differentiate between these two electrons? Because they are charged, their shape, size, everything is same. So we say that these electrons are moving in what? A higher energy band, which is called conduction band. To differentiate these electrons from those which are moving in low energy band, which is called valence band, we simply use the concept of hole movement. So what we say? Let's forget about movement of electrons. Let's say that positive charge which was present over here has moved to this new position. So now there are two types of charge carriers: free electrons which move in conduction and positively charged holes which move in what? Valence band. Hopefully you now can grasp the whole thing. Write down a few statements. When a photon interacts with an electron, when a photon interacts with an electron present in valence band, inside the bracket, forming a covalent bond, then if energy gained by the electron due to this interaction is at least 1.12 electron volt, for silicon and 0.7 electron volts for germanium, 0.70 electron volts for germanium, then electron will jump and enter into high energy band called conduction band. Inside the bracket, making itself free from the attraction of nucleus, thus becoming free electron. Now, because of the movement of this electron, silicon atom becomes positively charged. Because of the movement of this electron, silicon atom becomes positively charged, making itself more attractive as compared to other nearby silicon atoms. And because of this, an electron from nearby covalent bonds can jump and effectively neutralize the silicon atom which was positively charged, can neutralize it, but in turn transferring positive charge to that silicon atom it moved from this movement of electrons, takes place in valence band, and therefore to differentiate between free electrons, and these valence band electrons, we use the concept of positively charged holes. The whole thing in just two lines, write down two separate lines. Free electrons move in conduction band, whereas holes move in valence band. Now, this type of semiconductor, which is pure, only silicon is present, is your intrinsic semiconductor. These semiconductors are called intrinsic. There are no impurities present. You can write this also. When no impurities are present, semiconductor is called intrinsic semiconductor. Now let's see what happens when we add impurities. So what is the effect of impurities? Let's go into that. But before that, let me see if you have gone through this addition of impurity and all in your schools, or if you have done self-study or something like that. You know that I'm talking about p-type and n-type semiconductors. So tell me in the comment box, when we have p-type semiconductors, what is the charge on p-type and what is the charge on n-type semiconductors? Write down this in the comment box if you know about this thing. Some of you have answered, but let's see whether your answer is correct or not. Response is, which is normally I receive that p-type is positively charged and n-type is negatively charged. And there are always those who have answered nothing. There are those who know nothing. They answer never anything. You can teach them anything, but they will never respond. I've told you many a times that even if you answer incorrectly, you will remember that you thought this, but answer was this, and it will definitely improve your understanding. For example, those who have answered that p-type is positively charged, so when I tell them something different, they will remember this. So make a habit of answering questions even if they are wrong, because it's not possible that I don't think it's possible that somebody cannot think of these easy setups. So this is your pure silicon crystal. We are talking about extrinsic semiconductors. And in extrinsic, we are interested in P type. What is P type? You'll understand that. We are adding some impurities. So what impurity we are adding? This is aluminum. Aluminum has 3 electrons in its outer orbit. Everybody knows that simple thing. So aluminum has 3 electrons. When you add this 3 electron system, what happens? It replaces this. It can replace any, but let's say it replaces this. So once it replaces this, this is that aluminum. And this aluminum has 3 electrons. I hope you can see the color. If you cannot, this is red. These are the 3 electrons of the aluminum. Now what happens? These 3 electrons, they form 3 covalent bonds. 2 to 4 to 6. But it needs what? 8 electrons in the outer orbit for stability. Remember, there are free electrons present and as many holes are present. It was a pure semiconductor, pure silicon crystal. There are, let's say, 1000 free electrons and there are 1000 holes present in it. So free electrons and holes are present. This is the hole, this is the free electron. That's your free electron. In the conduction band, this is your hole over here. Now, this aluminum, what it does, it now attracts this silicon electron which is participating in this covalent bond. This electron is participating in a covalent bond. It moves and occupies this position. Once it occupies this position, this aluminum now has 8 electrons in the outer orbit. It becomes more stable than the electron. Basically, electron is becoming more stable. So this electron is becoming more stable as it moves and occupies this position. As it moves, this silicon becomes what? Positively charged. As this electron moves, this aluminum becomes what? Negative. But now listen, this aluminum which is negative is an ion. This aluminum ion is something which is not going to move. immovable. Once electron moves from this position to this position, it doesn't regrade this thing. It was less stable over here. Once it moves, it gains more stability. More stability, that means this electron is now not going to move. It's a fixed ion. Fixed. Immovable. It is not going to participate in conduction. It is not going to be part of current flow. It's a fixed ion. But due to the movement of electron, this silicon now becomes what? Positively charged. And positively charged silicon, you know, is called what? Hole. And this hole, we know that moves. Now, I told you that number of free electrons and number of holes, this is a hole, number of free electrons and number of holes, they are equal in pure silicon crystal. But once you added this impurity, once you added this trivalent impurity, what it does, it creates a negative ion which doesn't move, but it creates a hole. So now you have what? Excess of holes. You got an extra hole. This is over here, so just remember, you got an extra hole. For this figure, there is one free electron, there is one hole already present. Because of this impurity, we have created another hole. That means there is an excess of holes. Holes are positively charged, and therefore we say that it is a p-type semiconductor. The question I had asked you, that what is the charge on a p-type semiconductor? If you look at the charge, p-type semiconductor is still completely neutral. One electron, one hole, they cancel each other. Negative ion, positive hole, they again cancel each other. But this is a fixed ion, it is not going to move. That tells us that majority charge carriers are what? Holes. Since holes are more in concentration, this type or trivalent impurities create an extrinsic semiconductor of p type. Are you comfortable with this whole thing? But what is the meaning of p type? How come there is no net charge on p type, but it is still called a p type? Are you comfortable with this thing, yes or no? This is fixed. Write down the statement. When a trivalent impurity, like aluminum is added, it displaces a silicon atom and occupies its position. It displaces a silicon atom and occupies its position. But since there are only 3 electrons present in the outer shell, it needs one more to complete in all 8 electrons, which it does by capturing an electron, inside the bracket accepting, inside the bracket accepting. This kind of impurity will be called acceptor impurity, and later on we'll see donor impurities. These are called acceptor because they are capturing, accepting. So which it does by capturing an electron from nearby silicon atoms, thus making itself a negative fixed ion, which no longer participates in the flow of current, but has created an additional hole. The process of capturing has created an additional hole. That is when an acceptor impurity is added, when an acceptor or trivalent impurity is added, although the whole crystal is still neutral, we see that concentration of holes is more than that of free electrons. Concentration of holes is more than that of free electrons. Since there are more positive charge carriers, we call this type of extrinsic semiconductor p-type. Just a last figure. So this was conduction, this was valence band, this was conduction band. So when you are adding impurities like this, these impurities, they are close to this valence band region. This is your acceptor impurity energy level, very close to valence band. Valence band, conduction band, there is a gap. So this is the energy bandwidth for the added impurity. So for acceptor impurities, we see that they are close to what? Valence band region. close to valence band. And later on in the next class, when we'll talk about n-type, you will find that those n-types, they are closer to the conduction band. I'll note down this much, and rest we'll discuss in the next class. Note down everything and then you can leave. Thank you very much.